Let's continue our discussion on gradient descent, and in this video, we will learn about implementing gradient descent in Python. By the end of this video, you will be able to implement gradient descent in Python. Now that we understand the nuances of the gradient descent, we will move forward to implementing it. Implementing gradient descent can be tricky and cumbersome. For this, we will begin by defining a function for every step in the process of gradient descent. Note that we are implementing gradient descent for the sample data that we have been working with to keep things simple and clean. Step 1 is to initialize parameters. For this, we define a function called param_init. This function takes only the target variable as its parameter. In this function, we simply initialize m as a small value 0.1 and c as the mean of the target variable and then return them. Step 2 is to generate predictions. For this, we will define a function called generate_predictions, which will take slope m, intercept c, and independent variable x. This function returns a list containing predictions of every value in x with respect to m, c using the equation y equal to mx plus c. Step 3 is to calculate the cost. For this, we define a function compute_cost. As we know, cost is nothing but the mean squared error between the predicted and the actuals. Step 4 is to update parameters. As you can remember, this step is carried out in two parts: calculating the gradients and using the gradients to update the parameters m and c. So let's start by the calculation of the gradients gm and gc as per the formula we discussed earlier. For this, we define a function gradients which will take the predictions, target variable and the independent variables as parameters. The function simply computes the values of the gradients when given the values of all the variables. Next, we look at updating the parameters using gradients. For this, we will define a function called param_update, which will take m, c and gradients corresponding to them. We refer to them as old because we will be computing the new updated values and returning them. The code written in this cell is nothing but the formulation of updating the parameters as we have seen earlier. Now that we have finished defining functions for the different steps, we will define one last function called result, which will print the final result of the gradient descent. We will define this function by the name of result. This function will take values of m, c, independent and target variable, cost, predictions and iteration I as parameters. The first conditional statement checks whether the gradient descent converged with the maximum iterations we declared, or it ran through all the iteration and print the statement accordingly. In the second part of the function, we are first plotting the data points as scatter plot and then plotting the final regression line which we obtained from the gradient descent. Now we are completely set and all the nuts and bolts are with us. We just need to use them in the right sequential manner. Let's do that, one piece at a time. We start by reshaping our sample_data and renaming it to shorter, cleaner names. Next, we define some parameters of the gradient descent. We set the maximum number of iterations to be equal to 1000, initial cost_old to be equal to 0, learning rate alpha to be 0.01. Now we will perform the first step of the gradient descent. We will initialize the parameters of the gradient descent. For this, we will call the param_init function which we defined previously and pass the target variable sale_price to it. We will store the initial values returned by the function in the variables m and c. Next, we will define the loop which will repeat the rest of the steps until the maximum iterations declares or until the gradient descent converges. Now, we will be undertaking the step 2. For this, we call the generate_predictions function and pass the parameters m, c and the independent variable flat area to it. This function generates the predictions by using the equation y equal to mx plus c. We store the list of predictions returned into the variable predictions. The third step would be to calculate the cost of the model with parameters m and c. For this, we call the compute_cost function and we pass the predictions generated by the model and the target variable sale price. Now, if you recall, this function returns the mean square error of the model and we will store this value returned into a variable called cost_new. Previously, we talked about how to stop the gradient descent. For that, we define a conditional statement which checks the absolute difference between the cost_old and the cost_new. If the difference is less than 10 raised to the power minus 7, which is very low, then there is no point in continuing the gradient descent as the changes in the parameters are negligibly small. If the condition is true, we simply break the loop by using the break statement. Now that we have checked that the gradient descent has not converged, we calculate the gradients with respect to m and c. For this, we will use the function gradients. We will pass the predictions, target variable and the independent variables. The values returned by the function will be stored in the variables gm and gc. Now that we have calculated the gradients, we will now carry out the final step of calculating the gradients. For this, we will call the function param_update and pass m, c, gm, gc learning rate as its parameters. The function will return the updated values of m and c, which we will store into their respective variables. Now that we have completed all the steps of the gradient descent, we would like to see how the gradient descent works upon reducing the cost function and gradually updating the parameters m and c. For this, we simply define a conditional statement which will print the gradient descent report for every 20 iterations. At last, we update the value of the cost_old to that of cost_new. We maintain the cost_old variable to keep track whether the gradient descent has converged or not. And with this, we finally end our loop of calling the different steps of the gradient descent. At the very end, we simply print the final results by using the results function. So finally, our last cell looks like as shown on the screen. So let's run this cell and watch gradient descent in action. Something is definitely wrong. If you would notice, the values of m, c and cost are very large in magnitude, especially the value of cost is tending to infinite. This is not the result we expected. What do you think might have happened? This problem arises when we do not scale our data. Due to the large magnitude of the values, the cost generated by the model explodes in magnitude. To counter this, let's scale the dataset. Note that I am scaling the dataset using the standard scaler class right before we run the gradient descent. So let's run this cell again. Yes, now that is the result we were looking for. We can clearly see the cost decreasing every 20 iterations, and we can also observe the values of m and c gradually converging to their optimal values, and the cost is also being gradually reduced. You can see that the gradient descent converged after exactly 300 iterations. In the graph, you can clearly see the final regression line with the final parameters. Now, I would suggest you to play around with the values of learning rate alpha and the max_iter values and observe how they affect the regression line and the convergence of the gradient descent. You can download the notebook from the helper text below. So let's wrap up this tutorial considering that now we are able to explain the gradient descent both intuitively and mathematically, as well as can implement it in Python. We will be looking at the assumptions of linear regression up next.